Okay. Now, if you are going back to the previous lecture, we discussed about the three blocks or stages that an op-amp has in it. And you notice that the first stage is the differential amplifier. And we'll discuss, just the basic of this first stage, because we will go into the two different modes that we can use, the differential amplifier as the voltage source or the input voltage is applied to it. Now, imagine that, we have, the two identical transistors, the two identical resistors, and a single or a common resistor connected into the two emitters. And I will make, an assumption that I'll separate, the two transistors. That's, the left side, and that's the right side of the input stage of the differential amplifier for the op-amp. Now we can minimize, or we can model this differential amplifier stage as, an amplifier which has, the triangle shape with the two outputs. Remember that, the two outputs are in the collector voltage of the Q1, and the collector voltage of the Q2 is the output 2. Now, because they are identical transistors, identical resistors, now we are looking to determine what is the current that flows through the emitter resistor. And that's, the common current, which is actually provided by the Q1 and the Q2. Means that we can find the current that flows to the RE as the current that is supplied by the emitter of the Q1 and the current that is supplied by the emitter of the Q2. Means that the current that flows to the RE divided by 2, it will define the two emitters current, which is flowing through the Q1 and or the Q2. Now, in the same way, we can determine the value of this current, the IRE, which is the current that flows to the RE. The common resistance is the VE, which is a negative voltage, minus the drop voltage, the VE. Means that the emitter potential with respect to ground minus the drop voltage or the supplied voltage, which is the VEE, as a negative voltage source. The other voltage source that is supplied to the circuit, it's a positive voltage source, that's VCC. The identical transistors, remember that the two currents, or the two emitter currents, or the two collector currents are the same or are equal, and in the same time the two output voltages, the VC1 is equally the VC2. Now, the first assumption that we are making, we are connecting, the input 1 to the ground, and we are connecting the input 2 to the ground. Now, if the two inputs are grounded, and looks like, the two inputs is like, the inverting and or non-inverting inputs of the op-amps. If both inputs are grounded, the two voltages, the VC1 and the VC2, that's, the voltage at the collector for the Q1, that's the voltage, or the VC2 is the voltage at the collector of the Q2. The two voltages are the same and can be calculated as the VCC minus the drop voltage across R1, or the VCC minus the drop voltage across R2. Remember that the RC1 is equal with the RC2. Means that we can use, any of the two equations to determine what is the potential at the collector 1 for the Q1 or the voltage of the collector 2 of the transistor Q2, and those two voltages, it will be the same if the two inputs are grounded. You notice that to simplify this diagram, because I'm using a bit later to explain the different operations of the differential amplifier, I'll label as the output 1 or the output 2 as the two outputs of the differential input. Now, the next step is making, an assumption that I'm still having, the transistor 2 or the input 2 grounded, and I'm applying a voltage a positive voltage on the base. If a positive voltage is applied on the base of the Q1, what is going to happen? It will increase the collector current, which will make the output voltage or the VC1 to decrease or to be lower, which will cause the opposite side or the output of the Q2 to increase. Suppose that I'll make the same assumption, but in reverse way. Suppose that I'm connecting the input 1 to the ground, and I'm applying a positive signal or a positive voltage on the base of the Q2. Means that the same effect it will have on the two outputs. The output 2 it will decrease, and the output 1 it will increase. You notice that the amount of voltage of the output 1 and the output 2, one is decreasing with a certain amount, the output 2 is increasing with the same amount of voltage excuse me, as the other input is decreasing. Means that the two outputs, the output 1 or the output 2, it will increase or decrease with the same amount of voltage that is defined by the gain of the circuit. Now, a simplified diagram in order to see the behavior of the differential amplifier. That's actually the first operation, having a single-ended input. You notice that the input 2 is connected to the ground, but the input 1 is it has the voltage applied to it. Means that I'm looking to see or to determine what is the effect on the output 1 and the output 2. We just determined that if the input 1 is decreasing, that the Q or the VC1 or the collector voltage at the Q1 is decreasing, the voltage at the collector 2 is increasing. Means that the two voltages are increasing or decreasing with the same amount. The only difference is the phase shift of 120 degrees or out of phase between the two outputs, the output 1 and the output 2. In the same way, suppose that the voltage at the input 1 is decreasing or has a negative value. You notice that the output is increasing, and that's the VP of the output 1, and in the same way the output of the second transistor, it will decrease with the same amount. You notice that I will get the replica of the input voltage or the input signal, except that the two outputs of the differential amplifier, it will have a shift in phase by 180 degrees. Now suppose that I'll do the same, I will use the same voltage, the same signal source, and that signal source or the input voltage is applied to the second input. The first input or the input of the Q1 is grounded. Now I'm looking to see the effect on the two outputs, the output 1 and the output 2, as the voltage or the input voltage is applied on the second input. You notice that the as the voltage is increased. I'm at this stage, the voltage is increasing, on the second base of the transistor or the second input. It will decrease the output voltage, or it will decrease the collector voltage on the Q2, which will actually, or the effect on the Q1, the same voltage, it will increase the output voltage on the Q1. In the same way, we can look for the negative side, or when the voltage is lower than the ground level, the output 2 is increasing and the output 1 is decreasing, or it will have a negative value. Now the other way is combining the two single-ended inputs, and will end up with a double-ended. Means that I'm applying the two voltage sources, the V in 1 and the V in 2, simultaneously to the differential amplifier, or to the differential stage. You notice that the only difference is, the phase shift between the two inputs, and that's, the effect of amplifying the difference between the two inputs. Remember that it's a differential amplifier. What an amplifier does, it will amplify the difference between the two input voltages. But you notice that one is positive and the other one is negative for the first half of the period of the input signals. Means that the output 1, it will be twice the VP. Suppose that, I'm making the assumption that the amplitude stays the same as in the first two examples. The output or the output 1 of the differential amplifier, it will be the difference between the input 1 and the input 2. Means that as an amplitude, I'm looking for twice the peak voltage. Again, I suppose that the VP, it's a unity in the first two diagrams, and the amplitude on the differential double-ended inputs, it will be twice the voltage. Now I'll complete this sine wave. It will be twice the VP that we obtain in applying just a single input voltage to one of the two inputs of the operational amplifiers. Now, because of this assumption, and that's why I'm introducing the effect of having the voltage applied in one of the two inputs, and at the end I will apply two identical voltages, except that the two voltages or the two input voltages has 180 degrees apart, because now I'm going to move into the small signal. I'm talking about the small voltages and the signal analysis, or the signal parameters for an op amp. Now, in the same way, we can look just for the entire op amp. Now we are moving from just the differential stage, or the differential block, or the differential circuit, that is the first circuit or the first block in the block diagram of the op amp, into the whole the entire operational amplifier. Now we are doing the same thing. Suppose that we are having the operating circuit or the op amp, and we are applying the non-inverting input to the ground, and we are applying a small signal as the V in into the inverting input. You notice that as the input is increasing, or is positive, the output will be on negative. The double-ended mode, or the double-ended differential amplifier, has the same voltage source, but it's applied between the two inputs. You notice that in the first configuration, it's a single-ended, means that the voltage source is connected between one of the two inputs and the ground. For double-ended, the same voltage source or the same input voltage is applied between the two inputs. Means that one input, it will be the positive, the other input will be on the negative of the input voltage for a differential amplifier double-ended. Now I'm trying, to put, those, four possible modes together for a single-ended differential amplifier. The V in, or the input voltage, is connected to one of the two inputs, and the other input is grounded, or it's connected to the ground. In the same way, we can connect the input voltage to a non-inverting input, and the other input is connected to the ground, or the inverting input it's grounded. That's, the single-ended. You notice that one of the two ends, or one of the two inputs, actually has to be connected to the ground, and we are moving into double-ended differential mode. Now, you notice that if the two input voltages can be in phase or can be out of phase, we'll discuss, a bit later what is the problem having, the two input voltages in phase or out of phase, or 180 degrees out of phase between V in 1 and the V in 2. Now, in order to simplify, this circuit, or another possibility of having, the double-ended differential mode is applying the voltage source between the two inputs. Means that a small signal, or a small voltage, or the input voltage, is applied between the two nodes. On the other configuration, the two separate input voltages are applied between one of the two inputs and the ground. Now, the common mode. Now, in the common mode, you notice that that's differential. Now we are looking for a common mode. What means a common mode? Means that I'm applying, the same signal with the same polarity. And that's why I'm looking, for to emphasize, the common mode, because I'm moving into one important parameter of the op amps, the CMRR. What is a common mode? Means that I'm applying the voltage, the input 1 or the input 2, the same amplitude and the same phase shift. You notice that there is no phase angle between the two input voltages. Now, another way to look, in this diagram, suppose that I'm connecting the both inputs of the op amp, to the input voltage, which has, the same meaning as the other circuit that has two separate input voltage sources with the same phase apply to the two inputs of the op amp. Means that in either of the two cases, you notice that the same signal, the same amplitude, the same phase shift, or the no phase shift between the two voltages is applied simultaneously on the same input. Now the question is, what is the output voltage if I'm applying, the same voltage on both inputs? Think about, what an op amp does. It will amplify the difference between the two input voltages, but the two input voltages has the same magnitude and the same phase. Means that is the V in 1 minus the V in 2. But the two voltages are the same phase shift, means that the output voltage, it will be a 0 voltage because the two signals are in phase. And remember that what an op-amp does, amplifies the difference between the two input voltages. In the same way, we can look, for the second diagram or the second circuit, which has, the single voltage source applied, simultaneously on the two inputs. I'm looking, for 0 volts, means that this configuration is the common mode. That's why it's a common signal, common amplitude, or the same amplitude, the same frequency, and the same or in phase, or there is no phase shift between the two input voltages, which will cause the output voltage as the 0 volts. Means that actually, or practically, the input voltage, it will be canceled out. Means that, I'm obtaining, or ideal, it will be 0 volts. Now, that is the approach that it's made, to emphasize, the noise or unwanted sources. I mentioned that, and I put that in writing. Sometimes you'll see a noise, or what is the background noise. That's, the background noise, unwanted signal. Or radiomagnetic, radiation has, the same meaning. It's a noise that can be amplified by an op-amp, which will cause, or which will have, a background noise. But again, the same signal or the same noise is applied between the two inputs, which will cause the output voltage as being 0. Not always is 0. Again, that's, the ideal case when the noise or the unwanted signal is canceled if it is applied between the two inputs. And this value, must be kept, as low as possible. But again, we'll talk about, the CMRR as the common mode rejection ratio. Now, before I'm going into next step to explain and to define the CMRR. Now, one of the few important parameters is the AOL, the gain of an open loop. You notice that in this circuit, or up to this point, we didn't use any external circuits. Means that the gain of an op-amp is defined internally by the circuit, or the circuits that are used to build or to make, the op-amp. Usually, this value is very high. Ideally, it's an infinite value, but the specs of the 741, for example, is in range of 200,000. Means that it's a very high level of the gain. But again, that's an open loop. The A is for the gain, OL is for the open loop. Means that is defined by internal components, or the internal design of the op-amp. Those, values again are provided by the manufacturer, are in the specs of the op-amps, and the we cannot change, the internal design. We can use, an external circuit, and I will introduce today the feedback, or the negative feedback that it's used in most of the circuit. Sometimes it's defined as a dimensionless number, for example, 200,000, but most of the time is defined in dB. You notice that in dB is, one of the, convenient ways of defining a large number. Instead of 200,000, we can write is 106 dBs. But anyway, in this range, or around 106 dBs will be the open loop gain. Now we'll do some examples, and in the assignments or tests we'll see some numbers or some values closer to, or in this range, between 70, 90, 100, 100,000, which will make, you know, the open loop gain in a practical value. I'm not using, you know, any other values that we may see, you know, on some other circuit that has, you know, more than 200,000, the open loop gain. Now, going back to the common mode means that the same signal is applied simultaneously on both inputs, means that the rejection ratio, and that's the abbreviation for the CMRR, common mode rejection ratio. Now, the unwanted signal or the noise or the external signal, we don't want to amplify that. We want to use, you know, the amplifier to amplify just the useful signal, not the unwanted signal or the background noise or the white noise, sometimes is called in electronics. Is the unwanted signal that the amplifier has to reject. And that's, you know, the parameter of the an op amp, an operational amplifier, that will reject. It will actually nullify or will cancel the amplification or the gain for the common mode input voltage. Now, common mode rejection voltage, rejection ratio, which is, you know, we are looking, you know, to keep, you know, this value as low as possible, but we will see, you know, some practical values in terms of a large number or in terms of a small number. And that's, you know, the second parameter that it will be given, the ACM, the gain for the common mode, means that at this point or up to this point, we talk about the open loop gain, that's the AOL, which has, you know, a very large value and is defined or is given as a parameter in problems, or it's defined by the manufacturer. The other important parameter is the ACM, the gain in the common mode. Ideal, again, should be 0 because we don't want to amplify the common mode signal or the common mode differential amplifiers or the differential amplifier that amplifies the common mode signal. Now, how we can define the common mode rejection ratio? The ratio between the gain for an open loop over the gain for the common mode. I mentioned that those two values are given, are provided, means that we can calculate the CMRR as the ratio of the two gains, the open loop gain and the common mode gain. That's, you know, a pretty large number for the CMRR. But if we are looking, you know, to use the logarithmic scale, we can use, you know, 20 log of the AOL over the ACM, which is, you know, the gain for the common mode. Now, remember that the AOL is the open loop differential gain. Again, that's provided, that's given in the spec sheets of the op amp. The ACM is another parameter that is given by the op amp. Now, to explain again what means the CMRR, and I put an means that the useful signal or the signal that we want to amplify, we want to have, you know, a gain, we have to use, you know, this signal, it's amplified 100,000 more times, you know, more than unwanted noise signal. Keep in mind that, you know, this ratio, the AOL is very large, the ACM is very small. That's why, you know, the CMRR ratio, it's a dimensionless number as is defined by this equation. It's a dimensionless number because the AOL is dimensionless, the ACM is dimensionless, means that the CMRR is a dimensionless number. But what is representing, what is the meaning of the CMRR in a practical way. Again, I put an example. The CMRR is 100,000, means that the useful signal or the desired signal is amplified 100,000 times more than the unwanted signal. Now, an example how to calculate and how to use, the CMRR, and that's the practical example that I push to use the 741. I use the 741C. You may see A, B, C, some small variations of the 741, which slight change in some parameters in terms of the temperature, in terms of the gain, in terms of the supply voltage, and so on. Now, I mentioned that for 741, the open loop gain, that's the ACL, is 200,000. And the typical value for the common mode gain is 6.3. Means that we can make, the C to calculate the CMRR as 20 log the gain, the open loop gain over the gain for the common mode, and we'll end up with 90 dBs. That's a typical value. That's why I make an example to show you a typical value. Remember that in specs we have the minimum value, we have the typical value, or a maximum value. That's actually the typical value for a 741. The minimum value specified for 741, and I put that in writing, just to give you an idea, it's about 70. In our examples, we'll use some values that are closer to the practical or real values for those parameters, for the CMRR, for example. Some other parameters, but again, I'm not using intensively in this course, but just to show you, just to give you an idea about some other parameters. But again, those parameters are not used intensively in this course. The VOPP, remember that the PP is the power supplied voltages, and that's the maximum output voltage. Remember that we talk about swinging between the two limits, or the two or rail to rail, or between the two voltages applied to the op amps. That's the maximum output. And remember that the output voltage is actually based on the supplied voltage less by 1 or 2 volts in this range, just to give you an approximation of the output voltage, which is defined by the op amp, and is defined by the applied voltage or the supplied voltage to the circuit. VOS. Now, another parameter is OS, is the offset voltage. Now, always we need, to make a small adjustment. Sometimes is the differential DC voltage required between the two inputs to force the output to 0. We'll discuss about, how to have, an external component, an external device, or how to adjust or to force the output voltage to 0 when the same signal is applied on both inputs. And that's why I introduced already the differential single-ended and double-ended inputs. Biasing, as all the circuits requires bias, means that the current, or the biasing current, is the average between the two currents. And I mentioned that, those currents, has to be the same. Ideal, it's the same. Practical, it's a small difference, because nothing is perfect. And the biasing current, again, I'm not using, too much in this course, but, just to give you an idea about, some other parameters. The input offset current, the difference between the two currents, the I1 and the I2. In terms of impedances, yes, that's, the impedance and will calculate the input impedance, the output impedance with a feedback. But at this point, we have the differential input impedance, means that I'm looking into the op-amp between the two inputs. Another way to determine or to measure the input impedance is looking or measuring, the input impedance with respect to ground. That's the input impedance, that the Z-in, the common mode or with respect to ground, means that I'll measure, the impedance for an inverting input with respect to ground, and I can do, the same thing, looking or measuring the impedance of the op-amp with respect to ground, taking the non-inverting input. The output signal, again, looking, from the load point of view into the output of the op-amp, and I will measure that with respect to ground. Now we'll see, and we discussed about, some useful or typical values, again, for an 741, around, 100 ohms value for the input impedance. Another parameter is the slew rate. Actually, again, suppose that I'm applying, a step up voltage or a square voltage on the input. We have, different circuits, and we have, multiple devices or electronic devices, diodes, transistors, capacitors, which will delay actually the propagation of the input signal into an output signal. Means that always there is a delay and there is a small alteration in the output voltage as the input voltage is a step up or a step down. It doesn't matter. I can choose, the other way, or I'm applying, a step down, or it's a step voltage or a square wave voltage. Always, there is a delay due to the semiconductors and the capacitance between the base emitter, base collector, and the other diodes that are in the diagram, or in the block diagram, or the type of the op-amp that it's used. Now, the ratio of the change in the output for a given time means that how fast, or what is the delay time, or how it will propagate the input voltage as a step up or a step down on the output. Always, we are looking for making, the ratio of the change in output over the change in time, or how long does it take for the signal to be rise, from a lower voltage to a highest voltage, or vice versa, from a highest voltage to a lower voltage. And you notice that I'm having, a pretty linear slope, and sometimes, this slope, can be a bit larger, or can be a very small slope. Means that it will define the response time. That, response time is actually the slew rate, and in the specs of the op-amp can be defined as the dV0 to dt, and that's, the maximum response time. And that's, the example that I use, to make, a practical example. Suppose that we have, the ramp, or we have, the voltage or the swing voltage between the positive 12 and the negative 12. And if we are measuring, how long does it take for the output voltage to reach, the maximum voltage or the saturation voltage, which is, 4 microseconds, which gives, a voltage of 6 volts per millisecond. Pay attention, I'm converting, the microseconds into milliseconds, because, if I will keep, in microseconds, it will be a very large number. And that's why it's in 6 volts, per microsecond. Again, it will define actually the domain response, means that the response in time for a step up or a step down or a square wave signal that is applied on the input. Now I will try to introduce, and I'm using next week, the negative feedback. Now, going back to the ICS courses, did you use the feedback loop or the feedback signal on the ICS courses? Did anybody can answer this question? Did you use the feedback loop in the ICS courses until now? Okay, I will introduce the feedback topic and what is a feedback or a negative feedback. You'll use, the feedback loop or loops, cascading loops, bit later in the ICS courses when you'll see, multiple loops, in a system, to make the adjustment or to keep, the a process between two ranges or between two values as the mean and the max. And that's why it's probably pretty useful to introduce and use the network or the feedback or the negative feedback on a system. Actually, we are looking to have a small or a fraction of the output voltage return to the input voltage. Now, that's why I'm saying, a returning portion or a fraction of the output voltage, which is returned to the input voltage. And that's, the idea. Now, when the voltage is returned or the signal, generic signal can be voltage, can be current, it's a portion or a ratio of, or a small amount of the output voltage is written on the input voltage. Now the phase shift is the opposite to the input signal. That's why it's called a negative. Means that the output voltage, or suppose that the output voltage is positive, the input voltage is negative, or vice versa. Suppose that the input voltage is positive, the returning signal or the feedback signal, it will have a negative value. Again, I'm not looking for the amplitude. At this point, I'm looking for the phase shift between the feedback signal and the input signal. You notice that there is always an opposite phase, or the two signals are having the opposite values, the positive and the negative, or vice versa. If the input signal is positive, the output signal is if the input signal is negative, the output signal it's positive. Now in the op amps, we have to make an assumption. That's why I define as the golden rules for op amps. An op amp will attempt whatever is necessary to make the voltage difference between the two inputs as being equal to 0. Another golden rule, or another rule that we'll use in the op amps, and that's why I will define bit later a virtual ground in the input, or on the two inputs of an op amp, will draw no current. Means that there is no current actually drawing into the inverting or non-inverting input of the op amp. That's why you will see a bit slight different approach and different ways of the op amps rules, which cannot be applying the KCL, for example, and some other rules that we study in the linear circuits. Now, in this small And what is the purpose of a negative feedback? Again, we can control, we can manage, we can actually define or preset the output voltage to a certain, or the gain for the circuit to a preset value. Now that's a generic block. You may see something similar with the generic block with or using a negative feedback in some other courses, but at this point that is emphasizing the symbol for an op-amp as or a system, not only for the op-amp, a system that has an output voltage. The output voltage or a portion of the output voltage or the output signal is returned. That's the beta. That's like a resistive network, for example. And a portion of the output voltage, the output signal, is returned to the input. And now we have, a differentiator. We have, the difference between the two signals, the output signal and the input signal, which are, 180 degrees out of phase. Now, what's, the purpose of this negative feedback, or, feedback of the circuit? Even if it is, a very small signal, we are dealing with, 1 millivolt. And I made, an example. What is the purpose and, how we are using a negative feedback? Suppose that I'm making, or I'm having, a very small signal. The very small signal, which is, for example, V in as 1 millivolt, can be less than 1 millivolt. It doesn't matter, but multiply by 100,000 the open loop gain, it will make the output voltage as 100 volts. Means that I cannot amplify, this small signal with or using, the open loop gain, which is, I choose, one of the lowest AOL, or the open loop gain. 100,000 can be 200, can be 300, 400, and so on. Means that 100 volts is an impractical output voltage, and we cannot have the output voltage as 100 volts. Usually it's limited by the plus or minus 15, 20, sometimes 40 volts, but we are limited to less than 50 volts. We cannot get the output voltage to 100 volts. Means that even if it is a small amount of voltage, is 1 millivolt, or 100 microvolts or 10 microvolts, very small voltage, due to the amplification, the output voltage will be or the output will be in a saturation mode. Means that I cannot amplify, I cannot control this voltage. The advantage of a negative feedback, now we can control the gain. Means that I can have a precise amplification as 5.5, 10.93, and so on. A precise amplification. If I am applying the voltage on one of the two inputs, I can have a precise amplification of the signal using a negative feedback. Actually, those or negative feedbacks are defined by an external circuit. Actually, there are two resistors or a few other devices that can be attached or can be connected between the output and the input of the op-amp, in order to have a precise input or precise amplification or precise gain for the useful signal. Now, the increasing bandwidth. Again, we'll discuss about the next topic, which is next week we'll talk about the bandwidth and the advantage using the feedback or the negative feedback network and how to increase the bandwidth. It will increase the input impedance. It will reduce or decrease the output impedance. Now, the ACL, that's the third top or the third terminology or the third term that it's used in op-amps. The closed loop means that the op-amp is using an external circuit or an external group of resistors, for example, that it's used to reduce the output gain. Now, the last page, actually, I'll go over in the next lecture next week, because we are now at the limit of this class. Again, to remind you about the test on Friday, the same format as test 1, 70% long type questions, problems. I mentioned that it's about 4 problems plus or minus 1, and 10 multiple choice questions. Make sure that I have the student ID, calculator, pencil with you. Any questions, comments, concerns, please? If you don't have any questions, enjoy your day. Thank you, guys.